real-time adaptive controls for increased resiliency. We will get there. What that actually means, we will get there in the end. But first, I need to kind of make a sort of little note. Praveen was the one who submitted the idea for this talk. He's not really able to be with us purely because, personal reasons. I did think it'd be nice to call him out here. Thank you. Hope you're enjoying this on YouTube when it's not 6:30 for your body in the morning. I'm also going to give you a run through of what we're about to do. It's a 45-minute talk that gets pretty theoretical. So here's some landmarks for you to keep track by. I'm going to give you some context, talk about the issue. I'm then going to tell you why the existing solutions are just the worst thing. From there, I'm going to give you some tools to evaluate why everyone else is wrong and I'm right. I'm going to give you a solution that proves that I'm right. And I'm going to immediately contradict myself, show why I was wrong, and then give you some tools to show why I was wrong. From there, we'll just take all the tools we've gotten and use them in an exercise. Who am I? If you've seen that picture on the Gopher Slack, hi, I'm sorry. I've been working in software for about 8 years now, in gambling, telecom. I come from Brisbane, pretty sure I said that. And I've been working with CrowdStrike for the last 1.5 years to just make them go faster, make them less crashy. Who is CrowdStrike? Well, someone in this room would have gone to one of the 3 talks we had before us, right? Between Aparna's talk on testing, Tom's talk on how we should write HTTP clients, an accidental ad for IntelliJ, and Dylan's keynote on how we cope with modules. We stop breaches in Go at scale with a lot of data. Come work with us. Put me a referrer, please. So I'd like to talk about how much data we do use, right? That's the mug. I love this mug. It's my favorite mug. We got it for joining the 12 Zeros Club. Now, the 12 Zeros Club is, I think it was 1 trillion messages within 24 hours, which is now considered kind of slow, considering we're now clocking that at 15 hours per day on average. We almost clocked it in 12 hours the other day, give or take a few minutes, but still, we're doing an incredible amount of traffic, right? And as soon as you start to talk about this scale, you start talking about some interesting problems. So whenever I'm referring to the architecture, this is what I'm referring to, right? This is, in academic speak, command query responsibility segregation, or CQRS. Now, this is typically you'll have some form of message queue, something that'll read from that message queue and write to a database. And then in another process, completely separate, you'll have the information served out from some sort of reader over HTTP, or I think internally we use Morse code. So at the scale, in theory, this should work, right? However, it starts hitting weird problems. And to explain these issues, I kind of need to introduce 2 new characters. That's the shark. The shark is database node goes down. The shark is struck. Some sidecar in your containers booming. Oh, that's the shark again. The coffee on your desk goes cold. Oh, should have gotten to it before the shark did. The shark is the root cause of all faults within distributed systems, right? And it's just really a metaphor here, but you've also got the on-call, right? The on-call is, it's me, it's the team I work with. Hi guys. It's anyone working on your database at 3 AM, anyone who's got PagerDuty installed on their phone. And these 2 forces are always just in conflict. It's good for employment, it's a pain when you're at work. To give you an idea of what that looks like, I've drawn lines on a picture, hopefully to show it, right? Average day starts, the shark strikes, database node goes down. The on-call gets a page on PagerDuty, hey look, fix the database node, and everything goes back to normal. And in fact, they figure out a way to redirect traffic so the database can take more traffic from your app, and you get a gain in capacity. Shark strikes again. You've accidentally triggered a thundering herd against another service. And so you've got this contention between the on-call trying to fix the fires that the shark is starting, right? Now, most shops, like most places that you work, mine include, where I used to work included, had capacity requirements like this, right? This beautiful red line. So you'll occasionally get the story of, oh, the database went down and customers were on the phone and it was the worst. But you just get the company credit card and go, hey, Amazon, can I get some more EC2, please? Or you might even go, well, let's move from a CSV stored on a Raspberry Pi to Cassandra for our data store, right? And start relying on the fallbacks for that sort of stuff. The problem is, we've, yet again, 15 hours, 1 trillion messages, we've got high capacity requirements. So we can't just throw a credit card at it anymore. Like, did you know, and this is just, every time I think of it, blows my mind. You can max out the number of nodes in a Kubernetes pool. Like, there's a maximum number. You can't scale past that number unless you start splitting it out into distinct pools. So SRE was like, can we fix this at the application layer so we don't have to do this major infrastructure work whilst everything is down? So if I am a new developer and I've got this problem, I'll typically try back off and retry, right? So first, you stop, you take whatever's failing, and you just try again later. It's great. Typically, you'll have some form of delay when you try again later. So you typically call that jitter, and it's kind of very common if you search for jitter. You get tons of strategies on how to do it. Typically, you also have a max retries on how many times you attempt a message. So you might try 3 times and then throw in a pile for a developer at 9 AM on Monday to deal with. So running you through an example, you're trying to process 3 messages, and one of them is just touch too expensive for the database. It's just a cracker of a message. It fails. The writer then adds it to a retry queue internally, waits some amount of time, and then tries it again. Now, if your downstream database has the capacity to process that message, everything's fine, yeah? However, if it doesn't, well, that message there might have been okay usually, but you've got the capacity absorbed by this cracker of a message, this expensive one that's sitting right there and trying at the same time. And circuit breakers will mitigate this, obviously. However, we've accidentally created a negative feedback loop. So you've got your writer, sends through an expensive message to the database. Database tries its hardest for 2 seconds, goes, no, can't do it, sorry. Flicks it back to the writer. Writer will add it to the retry queue, and in some amount of time, we'll try it again, sending it across the wire to the database. Database will see that message plus your usual traffic and go, well, wait, I can't process 2 of you. Well, 2 of you can go back to the writer. Writer goes, 2 on the retry queue. Well, I'll send them both to the database. And use 2 failed, 3 failed, 4 failed, 5 failed messages. It just builds over time. There are strategies to work around this. As I said before, you can just give up. I love just giving up. In fact, but like, that's only pushing back the inevitable. Another strategy you can do is like, we've got exponential backoff jitter internally at CrowdStrike for services that don't need this special treatment, where you just go, hey, look, you failed once, try in a second. Failed twice, 2 seconds. Failed 3 times, 6, and just build up that time. But like, it should work, right? That shouldn't be happening with backoff and retry. I'm going to give you, to explain why this doesn't quite work, well, I've got a new tool for everyone. So here you go. When I said 45-minute academic lecture before, I wasn't lying. There will be a pop quiz on this afterwards. So this is Qing Theory 101. And Qing Theory 101 is L equals lambda times W, or the number of items in a queue, and is equal to how long they take in the queue multiplied by how often they're arriving, right? Great definition. Concreting it though, if you've got 4 messages coming in per second, you've got 1 message retrying per second, and they're all taking 2 seconds to process. Well, using some complicated maths that we're not quite sure of yet, you get 10 messages, right? And there you go. We've calculated concurrent limit on the downstream. Can't do anything with it though. Like, it's great during a post-mortem, but this doesn't help you when there's a fire. However, we kind of started wondering, can you just cap the number of messages coming into the system at once? And furthermore, can you go, well, hey, look, we're accepting 3 messages right now. Database is down. Let's just accept a few less. What would that look like? Well, drop the limit to 3. You've only got 1 times 2 because that's on how long it's taking. You only got 2 messages in your system. Suddenly got that capacity back because you've migrated off Raspberry Pis to EC2. Oh, hey, look, we'll bump the limit up to 100. We can have max 200 messages at once going into the database. How good is that? And the funny thing is about this is we already do this as SREs. So back to that graph of my average day, the shark strikes, and you've got the database person fixing the database. Old mate SRE is going to look at the drop in capacity and go, okay, I need to scale down. Explicitly or not, they're using Little's law to adjust the demand and capacity downstream by reducing the number of messages entering the system at once. Just before when I described DBA fixing the database and SRE redirecting traffic, well, SRE is going to also increase the capacity by filling it up so you can actually recover. It's great. And intentionally or not, using Little's law to adjust the number of messages entering the system. So there's a good chance you're already using this in your organization. I'm just showing you how we automated it. So sat around doing some thinking for a while, and then someone had the idea of looking at TCP congestion control. So after we hit up Wikipedia, we found AIMD, right? Additive increase, multiplicative decrease. So as an example, you'll have, back in the 80s, 200 years ago, you'll have your buffer of 5 bytes. You'll send that over the wire and go, hey, look, server downstream liked it. We'll try 6 bytes, 7, 8, 9, 10, a gigabyte, right? And as you're building up to that, you're seeing that downstream isn't dying. Let's try a little bit more. Very slow build. You then try and send a gigabyte. It's the 80s. What are you doing with a gigabyte? They didn't have a gigabyte to think about back then. Downstream goes, what am I supposed to do with this? Rejects it. The computer will go, okay, can't send a gigabyte worth of data. Let's try half. So you'll multiplicatively decrease or just scale back rapidly. And the interesting thing is, this is seen in so many natural systems. It's not funny. Ants, terrifying things. When they've found water and harvesting it, they'll slowly add more and more ants to that harvesting group until they find that some ants aren't coming back with water, and they'll just halve the amount of ants going for the water. It's in the room right now with us. Cell level homeostasis and how your body regulates temperature also uses something akin to AIMD. And the best thing about this is that's it. That's the code. That's all of it. PR is not accepted. It's old, it's reliable, and it's this battle-tested way to tweak the inputs into Little's law depending on how error-y downstream is. So if you look at this, and then you go, hey, wait, in TCP, they used to adjust the buffer size. What if we just squint, turn it sideways, and wrap a worker pool with this? I'm sorry to whoever wrote that Go Nursery blog post in advance. So obviously, this is literally what's sitting in there right now in my code at CrowdStrike. But it's really hard to see what that looks like over time. So I put some graphs. So limit. This red line is the limit. The limit is the number of things that can happen at once. I'm going to be using that word from now on. As over time, the server that's running this thing will go, okay, I'm going to do 1 thing, 2 things, 3 things, 4 things. I'll just count up and count up and count up until it reaches the capacity of downstream. It sees an error, and AMD is going to kick in and go, well, hold up, we're breaking something. Rapidly back off. Well then, hey, look, should be fine here. Build up, build up, build up, build up. Wait, we've broken something, back off. And what happens is you get this beautiful triangle oscillation around the perfectly static capacity. But capacity isn't static, right? So a more realistic example, you get your AMD building and breaching capacity, and halfway through a cycle, the shark strikes. The capacity drops off, and AMD doesn't notice the error yet. Builds up, until it does. And it has a moment. I'm not sure if they have Looney Tunes over here, but that moment where the character just kind of looks down and goes, oh no, the cliff's falling out from below me. It drops. It drops like a rock as it tries to do more and more, as it tries to do stuff. Can't. Getting errors, until it drops below the new capacity. And then it starts oscillating around the new capacity as it tries to do more, detects it can't do more, and then pulls back to do less. And then eventually, the DBA will hop off their Twitter and fix the database. And AMD will go, okay, I can do more. And then it'll just burst past where it used to have capacity until it hits the new one and then goes, oh, broke things again, back off. And it's interesting when you apply this to an incident, right? As I've shown before, right, each wrench here is actions that the like SRE or DBA or tech ops, if you're big enough to have your own data center, they're all interventions that people needed to do. However, when we implemented this, we reduced the work for the on-call for the application side by a ton, right? So some services at this point don't actually require intervention. You just let them be and manage everything else. You can think about like second order effects. Oh no, we're going to have a burst of traffic after we recover here, so we need to prep this area so it doesn't die, right? And it's pretty successful, right? So we're done. It's happily ever after finished. Thank you. So there's some problems with this. We're still at risk of taking out downstream, but when capacity is reduced, right? As I showed you with that graph, we're trying to push the database to its breaking point and they're going, well, mate, it was a joke, back off. And this graph here, it's fine. It's fine if you're talking like one instance, but when you're talking 50 or 100, they're all trying to actively murder the database, possibly during an incident, which is frowned upon, I'm pretty sure. Sorry. It's better now. We've gone from taking out the database to these little gaps. The database can recover in them. It does take time, but sometimes you'll still need to preemptively scale things up or down to kind of fix it. But we could do better. So went back on Wikipedia and I'm eating up on like chickens. We found AMD slow start. Now, I'm gonna be honest, slow start threshold the name is a lie. You'd assume that it's a slow start and then rapidly increase afterwards. It's the opposite. If you can see here, the limit rapidly builds, not multiplicatively, but still fast build until you hit this threshold, and then it's a slow build thereafter. Right, so it functions as a soft limit. So how's this look in code? Glad you asked. As you can see, it's a very simple change to the existing algorithm. There are a few issues with it though, right? You are setting this number, the slow start threshold, at startup. So if downstream capacity does degrade and you can't rapidly build to what you could before with your one instance, well, you're still actively killing the database like you were before, right? And also the number is per instance. So you have one of these things deployed with a slow start threshold 100, that'll rapidly build to 100 things at once. Yeah, database can take that. Cool, we'll scale up to 100. Can your database take 100,000 things at once? No, well, you're back into that thrashing loop of it trying to actively kill the database. Now, initially we were like, can we throw this into something like Redis memcached? But I'm kind of anti-centralization on a principle, so I thought we could do better, and we did. So here's the original code. Let's automate here's the original code. Let's automate the setting of that slow start threshold to be based on when we last saw an error, right? So between the assumed safe point and the known will break things point. So I'm going to pull up another graph just as a warning, but it's a very simple tweak that has a profound impact. So this is what it looks like now. So the slow start threshold could be some arbitrarily high number. It could be int max, maximum int 64. It doesn't matter. However, we build the limit rapidly, over time until we breach that static threshold. We get that first error. We fall back to some number that we assume is kind of safe. And we set the safe point to be in the middle. And then the next time we try that triangle oscillation that we were looking at before, well, we build up to that soft limit, and then no more growth. Slow down what you're doing. So you have this, I keep a hard gradient up, and then a slow build to the actual capacity after you pass that soft limit. And then it drops again, as does the safe point. So you start finding a lot more time to recover. So and as we know, like, capacity isn't static. So this will move when the shark strikes, and as the on-call fixes stuff. So that's one edge case solved. What else is there? Well, let me paint you a picture, right? On average, right, for Kafka, for most message queues, everything will take an equal amount of traffic, assuming you've set up partitions and everything correctly. However, moment to moment, that actually swings fairly wildly, right? So you might have rider A up the top. Well, everyone logs on at 9 a.m., so they get a huge burst at once of traffic. Rider B, the partitions it's reading from, or parts of the queue it's reading from, well, it's 3 a.m. for them. Why would they be up? So this is kind of interesting, right? Because it violates a lot of the expectations you'd have for a messaging system like that, although it's perfectly valid over an hour. Because over an hour, all of these will equalize out eventually. Right now, though, that one's getting smashed. One of them's getting smashed. One of them's seeing nothing. So when we plug one of the open source AMD implementations, what we're finding is it would see these bursts of traffic and then assume, hey, look, that's the high watermark. It's fine. I'll leave it there forever. That assumption there, where it's like, oh, high watermark is fine, that assumes the capacity is static. Now, like a lot of the other problems in this space, we need to look at this from the point of view of several riders. Each rider over time will have one of these bursts, and accordingly, one of these high watermarks that it won't test for over time. So you might get 20 here, and you might get 50 here, and you might get 10 there. If you get some sort of thundering herd or a message storm, or just lots of people finally use your service, well, your database is going to be hit by all of that concurrently, like the burst traffic from each rider concurrently. So over time, AMD will recover from that, right? However, it'd be nice to not start a fire rather than stopping it later. This can kill the database, and at our scale, that does take time to recover. So to explain the next solution, you kind of have to turn your programmer brains off for a second. And look, I need to talk to you about poultry, right? Chickens. So William Muir, old mate, way back when, was to study how do chickens perform when laying eggs, right? So he got a group of average layers, and they were fine at what they were doing. And they got a group of high performers, and the high performers doing 2-3 times. They were the 10x chickens of their day. And then over 2 generations, he watched these 2 communities of the mediocre ones and the high performers lay their eggs and breed, and to see how many eggs having high performing chickens would, like, how many extra eggs he'd get from the high performing group. And the average ones were consistent, and they got a decent amount from them, and most of the high performing ones were dead. So the issue there was they were competing for resources, and that contention over resources ended up killing most of the group. I'm not going to mention how, it's pretty grisly, don't look it up. But this whole idea of like having a group of high-performing things competing for resources, destroying the system as a whole. It's called the super chicken model, and you can misapply this in so many ways, right? So like Brisbane traffic. I know you are here for GopherCon, but this is more important. Locally, we've got in our highway system, we're dropping the speed. So moment to moment, you're going slower from like 60 miles to 50 miles, I think it is. Moment to moment, you're going slower from point A to point B. However, that one change is alleviating congestion on the off-ramps, which means there's less traffic, which means traffic accidents are rarer. So most people are spending less time on the highways, even if they are going slower, right? And the initial application of this, like most things, was from a business magazine. where they were talking about don't hire too many high performers if you don't have the resources for it. So letting each rider compete for and be as performant as they could be, like the high watermark setting before, it makes them try to dominate resources, which ends up killing performance for everything, right? And the solution was simple. Barney taught us it, right? It's to share. So each rider will willingly scale back how much it's using at once, how much it'll assume it can use in future over time. And the funny thing is about this, it opened up our eyes to an interesting source of waste. So we were looking at it, and we had CPU usage of like pretty constant between riders. However, we had groups of 10 to 20, groups of riders using 10 to 20 limit. However, and that's like, you'd assume that's the same as 30. One rider with a limit of 30, right? So in theory, you can collapse these three down to one. What the implication of that, right, is you've got three processes you're not paying for anymore. You're just paying for one. If each one of those processes is using some amount of CPU for the Go runtime, some amount of CPU for the Bitcoin miner, some amount of CPU for like just scheduling for Kubernetes, well, you've gone from paying that 3 times to paying that once. What that looks like in reality is like a 40% reduction in resource usage across like one of our bigger clouds for a pilot service. And that's good. That's an explicit gain though. That's an explicit gain. There is an elephant in the room though. I'm kind of skirted around it before. I did say I was morally opposed to it. There's still no coordination between processes, right? There's a database there. It can only take so many things at once. Throw the number in Redis, throw it in memcached. We should just be able to make this work, right? Have it centralized. But that's the lack of centralization is actually a feature. All right, so I'm generous. I'm feeling generous. I'm gonna give you a new tool. See, I told you a lie before. This is CQRS. Looks great. Looks really nice when explaining it on a stage. However, if you pull back the covers, that's what it looks like on the micro scale. And this is just the read side, right? So each one of those riders is going to have a different idea as to what capacity is going to be, depending on what data they're currently processing in the database node that it's destined for. And it's impossible to have, because of that complexity, it's impossible to have this unified number. It's going to be a white lie. And as much as that's nice for an OKR, it's not nice to run a fire off. But luckily, someone named Ashby already has an idea on how to deal with that while studying homeostasis. This is Ashbys Law of Requisite Variety. It's not actually Ashbys Law of Requisite Variety. That one's about 3 paragraphs and be conference friendly. But the more convenient definition is that the issue for a system to be stable, the number of states that its control mechanism is capable of attaining must be at least greater than the number of states that the system of the states being. It's up there. You can read it. In other words, you can have either, for the writers, you can either have too many requests, it's doing too much, it's doing too many requests at once, or it could do more. And that's 2 states. An integer holds more than 2 states. So it's a good fit. It works. However, if you pull that control mechanism out from the process and into a centralized database, that control mechanism, whether it be an external service or some library in each one of the writers, needs to be aware of every other writer and be aware of their 2 states. And this adds a ton of complexity that's not really needed. Sorry, and sorry, I just need to go back and going off script for a second. We found that in practice, each one of these writers will do different amounts of work depending on the nodes that they're talking to over time. So you can have a partial outage now, which is pretty neat and pretty painful, where you'll have writer A and B not actually have any degradation of service at all, purely because they're talking to the good database nodes. Writer C will have some issues, but it's not impacting your whole deployment. It's just impacting 1 or 2 things. Sorry about that. So, well, I'm just trying to explain. We went with the latter, and it is so much more complicated when you're looking at it from the outside in. But because it's bottom up, you can kind of just let it run and it just works. And that's what's currently managing our capacity between, I think it was thousands of deployments and hundreds of deployments, thousands of containers. And it's currently keeping me off PagerDuty and on Twitter. And that's the most important part in the end. So by now, we've got a couple of tools, right? We've got Little's Law, AMD, we've got our super chicken model, and Ashbys Law of requisite variety. Really fun to say. Let's just use them on an arbitrary problem that no one's seen before, right? So HTTP rate limiting. The standard for rate limiting isn't great, right? It usually gives clients some static numbers or some static requests per second to use against your system. But that assumes the capacity is static, which if you take one thing away from this, capacity isn't static, please, for the love of God. So by this point, we also know that the reader itself is going to have multiple instances deployed across probably data centers, right? And talking to different database nodes, and it's a mess underneath there. Static capacity isn't going to cut it. So let's see if we can run it through Little's Law, because if we can then use the queuing theory against it, and we can just take the thing I talked about earlier and just plug it in. So you squint, look at it sideways. You can argue that the number of concurrent requests is equal to the number of inbound HTTP requests at any point multiplied by how long they take. Stuff it, looks good enough. Let's AMD it. So if you did do this, don't sign contracts on it, please. I'm not going to be held liable for this. And you will need to do some finagling in memory. Don't know how I know that, but you will. But this does give us a way to restrict the concurrent load per reader. And since we've got a way to measure capacity, we still need to allocate it to clients, right? So let's see if we can just allocate some percentage. So if client A is really important and your reader can do 100 requests at once, well, hey, look, give client A 50% and they can do 50 at once. Client C is the intern project. It's important, but it's not business critical. Give them 10. If a reader can do more, we'll increase the number of requests. Client A can do it once by the same amount, right? So if the reader can do 1,000 things at once, client A gets 500 requests at once. If the reader can only do 10, client A gets 5 of them. So this is a really neat solution, right? It kind of solves a few issues, but it doesn't fix the chickens, right? What we're doing is we're forcing these clients to compete for capacity, not at runtime, but when their developers are talking to other developers and going, hey, look, can I get, you still got the competition. And it just ends up with bad feelings and hurt friendships and bad feelings rather than anything else. So can we force the super chicken model into this? Well, yeah, we can. If a client isn't using this full capacity, we can just share. So as an example, I don't know if you guys have birthday parties over here. Do you have cake? Some kids will get a little bit more because they're the birthday boy. And, well, other kids won't feel like cake. If someone comes along for another piece, you don't say, no, kid who's not having any, that's their piece, go away. You go, sure, why not? Other kid's not going to have it today. You can do the same with these clients. So client A gets 50 concurrent requests. Intern project is getting a little bit excited and needs a little bit more space. It needs a little bit more than the 10 concurrent requests. It needs 15. Client A doesn't need all of the concurrent requests right now, so just let them use it. So you'll find. So what happens there is you get this point where you'll still have contention for resources when everything is down, but these clients won't actually step on each other's toes when everything's okay. And it's very, very, very smooth in that way. And mostly because this accidentally satisfies Ashbys Law. So each reader, has I can do more, or I'm doing way too much, I need to scale back, right? Each client, because it's a rate limiter, has I can do more, or I need to chill out. And according to the tools we have, and all the complexity that you need to satisfy Ashbys Law comes in the interaction between client A needs 50%, Reader only has 10 requests to give. Are you using more than 5 requests? So the complexity is emergent rather than isolated to a single place where you need to sit down and figure it out at runtime. So according to the tools we have, this should be a decent solution. And when we deployed it, we actually found it worked really well. So we used to, sorry, tangent, when in our SRE help channel, we had to get people asking for rate limit increases. They weren't coming, but they weren't anymore, purely because we taught the server how to share. And this is how we've deployed rate limiting to some of our critical HTTP APIs, and it's working beautifully. So moving forward, I hope that you consider like these humble tools when looking at how to design your next service. If my time at CrowdStrike so far has taught me anything, it's that reliability doesn't really end at the boundary of your service or even your team. It ends when the client request is finished, or when you finally got that Kafka message in the database. No sooner, no later. And every one of us in this room is responsible for that in the end. Oh, and careful of the shark. Thank you.